Let's go over notes for 7.2 Part A. We started 7.1 with area, but now we're going to expand that idea to volume, and this is volume by disk method. Let's review what we've covered so far from 7.1. Let's say we have a region, y equals square root of x, and we're looking at that region between the graph and the x-axis, and here is the shaded region. And between 0 and 4, we have our bounds in place. We draw a representative rectangle that connects from one boundary to the next, and the top of the rectangle is where we can identify the top function, and the bottom of the rectangle is where the bottom function resides. So we do top minus bottom, just like how we applied with our area formula. Our bounds are from 0 to 4. Top graph is the root x minus bottom graph is the 0. So root x minus 0 is just root x. And if we plug this in our calculator or work this out by hand, we get area of 5.33 repeating square units. Okay. I also want to emphasize the fact that from a visual perspective, we're also working it out this way, where the root x minus 0 represents a certain height of this rectangle, right? Because root x minus 0 is going to be slightly different here versus here, but they all kind of give a basic formula for all these rectangles. And that's what's happening, is that we have the height of the rectangle represented by the root x minus 0. The dx notation gives it that width, that infinitely thin width of each of these rectangles. And once we have the height and the width component of these rectangles, that produces area, right? Because area of a rectangle is width times height. But that only accounts for one of these thinly drawn rectangles. We want to find the area of this full region, and so that's where the calculus, the integral notation comes in. The integral from 0 to 4 essentially accumulates all these separate and infinitely thin rectangles from one end to the next, and the accumulation and the stacking of all these rectangle areas will achieve the full area of this region. So this integral calculus notation allows us to add these infinite numbers of these differently sized rectangles to form or to give us that area calculation, right? So the reason why I want to specify using this explanation is to draw the connection between area and this first volume formula that we're going to talk about, which is this method. Okay, so here's the start of this method. So let's say we start with this region. Okay, let's say we're dealing with the same region, but rather than stopping here with this two-dimensional shape or two-dimensional region, we're going to create a new object out of this region. And the way that we're going to create a new object is we're going to rotate this expression, or sorry, rotate this region 360 degrees around a certain axis. In this case, we're going to call it the x-axis. So as we rotate this all the way around this x-axis, can you guess as to what shape that we're going to create if we were to take this resulting object into thin slices? Okay. And the answer is we're going to be achieving these circular disks. Okay. So imagine taking this two-dimensional region, and let's say we rotate this 360 degrees until we create a shape that looks like this. Looks like a half a melon or half a potato. Basically, we can think of it as this solidly compact object, three-dimensional object, that visually we can think of as adding infinite numbers of these circular disks from one end to the next. So rather than adding infinite numbers of rectangles, we're now going to adapt this concept to circular disks, which will move us from a two-dimensional area calculation to a three-dimensional volume calculation. Okay. So I want us to be able to think of these as circular disks, right? And the idea of circles is going to be important here. Let's take one of these disks, for instance. Right. The dimensions of this disk obviously is we have the area of a circle component, right, as the face of one of these disks, and the area of a circle is pi r squared, right? That's the area formula for circle, and that gives us that two-dimensional calculation, that two-dimensional value. But we're going to give it this circle a certain width, and that width is represented by dx. Much like how we were using the width before to give the rectangle that second dimension, that height, that second dimension. Now the width here, this dx, is going to give this area, this two-dimensional value, a third dimension, a width component. So if we start off with pi r squared, right, but rather than calling it r, we're going to call it r of x. And r of x is going to represent a certain radius function. Okay? And that radius function is going to change from one end of the object to the other end of the object, because we're going to have these differently sized circular disks, all with different radius. So we'll use big R of x to represent the area or represent the radius of the circle, but we still have the pi r squared as part of the formula. So we have a two-dimensional calculation that we're going to give it that third dimension, and that dx will give it that third dimension. So now this pi big R squared dx will give us the volume of one of these thinly sliced circular disks. And now if we want to achieve the full volume from one end to the next, where we're going to stack these circular disks from one end to the next, we're going to be introducing that integral notation. So that integral notation is going to do the same thing that we did with these rectangles. Rather than stacking infinite numbers of rectangles, we're now going to stack infinite numbers of these circular disks from one end to the next. And this integral notation will now allow us to find the full volume of this curved object. Okay, so let's look at one or two examples on the next page here. So the steps that we're going to do, we're not going to be having to draw these objects. We just have to be able to identify the parts that will form the formula or the values that we need to plug into the formula. So the first thing we do is we're going to draw a dotted line across the x-axis to indicate that location of the axis of revolution. Now the axis of revolution is not always the x-axis, but this first problem we're going to be working with the x-axis. Okay. The problem will always tell us what the axis of revolution is, and we're always going to be drawing a dotted line across that axis. Sometimes it's the x-axis, sometimes it's going to be a different line. The next thing is we're going to draw that length of that radius. We're going to place our pen or pencil first on the dotted line and extend to the outer boundary of the shaded region. And once we have our radius drawn in place, we're going to calculate that calculation the same way that we did with rectangles for area. We're going to do top graph minus bottom graph. We're going to identify the left and right bounds the same way. If needed, we're going to set the equations equal to each other to find those bounds if the bounds are not visibly noticeable. Once we have our radius expression, once we have our bounds, we're going to put into our volume formula for this method. And the rest, we're going to use our calculator, either using the TI-84, TI-36, or we can use the online calculator. Right, so let's look at example 1 here. It says find the volume of the solid formed by rotating the curve y equals square root of x around the x-axis between 0 and 4. So this is the same object that we dealt with on the previous page, just that now we're working, going through the steps to actually find the answer to this particular volume of this object, of this curved object. So first, it's revolving around the x-axis. So we draw a dotted line, indicate that as axis of revolution. We have our shaded region. We're going to start, put our pen or pencil directly on the axis on the dotted line. We're going to extend to the boundary on the other side of the shaded region. And we're going to create a rectangle, but that rectangle doesn't represent the height of a rectangle anymore. This now represents the radius of a certain circular disk that we're rotating. Okay. So then we do top minus bottom. The top is sitting on the root x. The bottom is sitting on the 0. So root x minus 0 represents this particular radius that I have drawn here. Now if I draw it over here, it's also root x minus 0. If I draw it over here, it's also root x minus 0. We're just going to make the calculator do the rest of the work of accumulating all these disks from one end to the next. Our bounds we can clearly see as going from 0 to 4, and also it's indicated in our problem. So now we're ready to put into our formula. Pi is going to be a constant. We're going to have that out in front of the integral. It's just a coefficient. It's not going to affect our integral notation. Our bounds from 0 to 4. And then we're going to put this root x into this location of that r of x. So our formula will be r of x quantity squared. So whatever you put inside your radius expression, we always want to make sure that we're squaring that full expression to give it that pi radius squared, to give it that circular dimension that it needs, since we're adding these shapes that are circle related. So when it gets put into the when it gets put into our formula, we have pi integral from 0 to 4 radius squared. So root x squared cleans up to be just x. This is easy enough for us to work out by hand, but we can also enter in our calculator. Now when we enter in our calculator, you're going to enter it without the pi notation. So in your calculator, you'll just do math 9 or definite integral from 0 to 4 of x dx, and then that will just give you 8. And whatever number you get, if you need to convert to a fraction, you can, but then you're going to physically add that pi to your answer. You're not going to enter the pi in the calculator. If you do, you'll just get a decimal value, and we're just more interested in trying to find an exact value. So you'll leave the pi out of the calculator, and you'll just add that in yourself at the end. Okay, example 2. Find the volume of the solid bounded by the x-axis, bounded by the y-axis, bounded by the curve 4 minus x squared. That's the parabola that opens down. Negative x squared indicates it's a parabola that opens down. Rotated around the x-axis. So again, our axis of revolution is the dotted line that we can create right on the x-axis, this y equals 0 equation. We're going to rotate this shaded region around this axis. So we're going to extend from our axis of revolution to our boundary, and that is going to represent the length of our radius. Once you have our length of our radius, we're going to do top minus bottom. The top of the radius is sitting on the 4 minus x squared. The bottom of the radius is sitting on the 0. So we have 4 minus x squared minus 0, which cleans up to be just 4 minus x squared. All right, I think we have everything that we need. We have our bounds. We can clearly see from 0 to 2. Those are the furthest left to furthest right of our x values. So 0 to 2. And we have our radius in place, so we'll put that in place of this r of x. But we'll put that in a set of parentheses because we need to make sure we include that squared as part of our area formula. So this is what our equation, our formula looks like, and the rest goes in our calculator. So in this case, I can do math 9. So math 9 will take me to my FN integral. I'm just going to plug everything in as I see it. Leave the pi out of my calculator. I'll go from 0 to 2. Parentheses 4 minus x squared. Okay, X button is right near the top here. Close parentheses squared. That's my radius quantity squared. I'm going to fill in that dx there. Hit enter. Now this is a decimal value that I can convert to a fraction. So if I do math, fraction, enter, math 1. And now I just have to use my pen or pencil to just include that pi at the end of my answer. So 256 over 15 pi cubic units. Again, we leave the pi out of the calculator, and we're just going to manually enter that in ourselves.